Okay, in this tutorial we're looking at section 11.7, which is on Euler's method. Okay, a lot of people mispronounce his name and say Euler, but it's actually Euler. He's a famous mathematician. It was around in the 1700s, okay, but it's Euler, not Euler. Okay, there are some first order differential equations that cannot be solved because the integration cannot be done. Okay, the solution can be approximated using numerical techniques. Okay, Euler's method is used to repeatedly iterate our equation here. Okay, so y of n plus 1 equals y of n plus h of h times f of x of n. Okay, where dy dx equals f of x. Okay, and y of x naught equals y naught. Okay, we have a value for h. Okay, is our step size or difference between x values. Often this will be like 1 or 0.5 or 0.25, something like that. The smaller h value that we use, okay, the closer our approximation will be. We also need a value for x naught, so our initial value for x, and y naught, the initial value for y. So we need these first bits of information to start off with. Okay, when we have a type 2 differential equation in the form of dy dx equals f of y, then we use y of n plus 1, which equals y of n plus h times f of y of n. Okay, when we have a type 3 differential equation in the form dy dx equals f of xy, we yi of n plus 1 equals y of n plus h times f of xn and and yi. Okay, so this is really best demonstrated through some worked solution. Some worked examples. Okay, so we're going to have a look at worked example 1. Okay, so we need to use Euler's method to tabulate the solutions to the differential equation dy dx equals 1 over x squared plus 4. Okay, we know y of 0 equals 0. Okay, and we know h equals a half, and we're going to approximate y of 2. Okay, so when we have a look at this, so we're approximating y of 2. Okay, so that's going to be when x equals 2. That's what we're approximating. Now we know that x naught equals naught and y naught equals naught. Okay, and of course we know that our h is a half. Okay, so since we're starting at x naught equals naught and going to x equals 2 with a step size of a half, we're going to have to do the procedure 4 times. Okay, so what we're going to do then is say, well, y1 equals our y of naught plus h times f of x naught. Okay, so what we've got is we use this dy dx, we say that's our f of x. Okay, so if we do this, we're going to say y1 equals y naught, well that was 0, plus our half outside of our f of x naught, okay, which is 0 there, so it's going to be times a quarter. So y1 equals 1 on 8. Okay, so that means that our y2, because our y1, sorry, plus our h times f of x1. Sorry, yeah. Okay, so our y2 equals our y1, which is our 1 on 8, plus we've got the stating h value of a half, okay, times our, this time we're going to have our f of x1, okay. Now x1 was our, going to be our half, because we're going to keep going up in our step sizes of a half, so now we're going to put a half into our equation, so it's going to be a half squared plus 4. Okay, so that means that when we do this, we're going to get a value of 33 on 136. Okay, and that's our y2. Okay, so then we're going to do our y3 equals our y2, which is our 33 on 136 plus a half. Okay, this time we're going to use our next x value, which is going to be 1. So it'll be 1 over 1 squared plus plus 4. Okay, so it'd be a fifth times a half. Okay, so we get 233 on 680. Okay, Then we'll keep going. So that's our y3, so our y4 then, it's going to equal that 233 on 680 plus a half times our 1 over 1.5 squared plus 4. Okay, it's going to give us 1,437 over 3,400. Okay, so our y of 4, our approximation, is 0.4226. Okay, and so that's going to be our approximation. Okay, it's our fourth one. Okay, so that's our approximation. Okay, for x equals 2. Okay, so we don't actually use our x equals 2, okay, in the step to get the approximation for when x equals 2. We only have to use that x value prior. Okay. Now, part B is solve the differential equation, so the one that we've got, okay, and to determine the actual value of it. Okay, so this is one where we can actually do it. Okay, so what we're saying is our dy dx equals this. So our y is going to equal our integral of 1 over x squared plus 4 dx. Okay, which means we're going to get y equals a half times the inverse tan of our x on 2. Okay, plus our c value. Okay, but we know that that our c is going to be 0. Okay, because our x and y are 0. Okay, our initial values are 0, so we're going to say c equals 0. So we're going to say y equals a half times the inverse tan of x on 2. Okay, when we and then we say, well, let x equals 2. Let's get the actual solution is what we're chasing. So we need y equals a half times the inverse tan of 1. Okay, so when we do that, we get a half times pi on 4. Okay, which equals pi on 8, which is approximately equal to 0.3927. Okay, so we need to look at our, they also asked us to look at our percentage error. Okay, so that's what we got. So percentage error, right, is equal to what we got, 0.4226 minus what the actual value is, 0.3927. Okay, over what the actual value is, 0.3927 times by 100. Okay, and when we do that, we find that we have a percentage error of 7.6%. Okay, so a little bit out. Okay, but if we'd used a smaller h-step value, okay, that half, if we'd done it where it was smaller and we'd done more iterations, okay, we actually would have been closer to it than what we actually had. Okay, because our values here would have been closer as we went through. Okay, so that's the idea. It's similar to doing Newton's method or the bisection method that you would have seen at some point in math methods, whether it was this year or last year. Okay, you would have seen that at some point. Okay, so we'll have a look at worked example 16. Okay, so this is for type 2 differential equations. Okay, so this time we're going to use Euler's method to tabulate the solutions to the differential equation dy dx, okay, minus e to the negative y equals 0, okay, y1 equals 0, okay, for h equals 1 on 4 to approximate y2. Okay, so they want us to do an actual table here, which we should have done last time. It's probably easiest to set it up like this, because then you can keep track of everything. So we need our x and our y. Okay, and we're going to need our, probably not going to have left enough room here, so we need our initial one, which was, what we know was x equals 1, y equals 0. Okay, then we're going to need it for 1.25, and we need it for 1.5, 1.75, and of course our 2, which is what we're trying to find. Okay, so we need to rearrange this a little bit and say, well, our dy dx is equal to e to the negative y. Okay, so that means that our f of y equals our e to the negative y. And as I said, x naught equals 1, y naught equals 0, and h equals a quarter. Okay, so we can set up our equation now. So again, we go our y1 is going to be our y naught, okay, which is our 0, okay, plus our HO, which is a quarter, okay, times by our f of y naught, which is 0. Okay, so 0 plus a quarter times f of y naught. When we put 0 into here, we get e to the 0, which is 1. Okay, so we get a y1 value of a quarter, okay, or 0.25. So when we do y2, okay, we put in this value to start off with, which is our 0.25 times a quarter, plus a quarter, okay, and we need to put in our y value we just got, okay, so it'll be e to the negative 0.25, okay, so then we get our value there of 0.4447. That's what we get for here. Okay, so that's our starting point for our next equation. So our y3 equals 0.4447 plus our quarter e to the negative 0.4447, okay, which gives us the value of 0.6050. 0.6050. That's our starting point for our next one. y4 equals 0.6050 plus a quarter e to the negative 0.6050, okay, which gives us a value of 0.7415. Okay, so again, if we'd actually gone through and done a smaller h size, we'd end up a bit more accurate. And again, we're going to do the same thing of actually solving this and then comparing our results for part B. So we say that our dy dx is equal to our e to the negative y. Okay, so our dx dy equals our 1 on e to the negative y. Okay, so that just simply equals e to the y. Okay, so we're then saying, well, our x equals our integral of e to the y dy, okay, which is equal to e to the y plus c. Okay, so we know x equals 1, y equals 0. Okay, so we say 1 equals e to the 0 plus c. E to the 0 is just 1. Okay, so we can see there that our c is going to be equal to 0. So we can just say x equals e to the y. Okay, so y equals log to the base e of x. Okay, if we need to sub in our 2, so we get y equals log to the base e of 2, right, which is going to equal 0.6931. Okay, so we have a look at our percentage error. I'm going to say, well, again, we're going to be 0.7415 minus 0.6931 over 0.6931 times by 100 is a percentage error of 7%. Okay, so as I said, if we had a smaller h value, then we would have actually got a more accurate actual answer there. So we've got one more worked example to do, which is for a type 3 differential equation. Hey, so this time we've got dy dx plus 2xy squared equals 0. Okay, y naught equals 2. Okay, h equals a quarter, and we've got to find y1. Hey, so again we say our dy dx is equal to negative 2xy squared. Okay, and as we said, y of naught equals 2. Okay, so we need to set up our equation. So we say y1 equals y of naught, okay, plus h times f of x naught y naught. So our initial one, y naught was equal to 2, okay, plus our h value of a quarter, okay, times our function with 0 and 2 in it. So we go and say, well, we've got minus 2 times our 0 times our 2 squared. Okay, well that's going to be 0 anyway. Okay, so it's going to equal 2. So this time, okay, what we're going to do is we're going to say, well, y of 2 equals our 2 plus 1 on 4, times by our minus 2, times by this time we've got a h step of a quarter. Okay, so that's our quarter, this is our x values. Okay, and then we've still got our y of 2 squared. Okay, that we had there. Okay, so now that's going to equal 1.5. Okay, so then our y3, okay, equals our 1.5 plus a quarter times by our minus 2 times by a half times by 1.5 squared. Okay, which is going to give our next value of 15 on 16. So then our y on 4, which is our last one, I would say that's approximately equal to 0.9375. So we'd say our last one is 15 on 16 plus our quarter, okay, outside of our minus 2, times our 3 quarters, because we have to go up our h step again, okay, times by our 15 on 16 squared, okay, which is going to give us a value of 1,245 on 2,048, which is equal to 0.6079. Okay, so if we did our little table up, our x and our y, okay, so we know with our y value, so we know when we started we were 0 and 0, okay, then we were 0.25, okay, and we were 2 again, then we were at 0.5 and we end up with 1.5 we had, then we end up with 0.75 and our 0.9375, then we end up with our 1, which is our 0.6079. Okay. So again, they want us to solve the differential equation to have a look at what we would actually get in our percentage error. Okay, so we say our dy dx is equal to our minus 2x y squared. Okay, so that means that we've got our integral of minus 1 over y squared dy equaling our integral of 2x dx. Okay, which means we end up with our 1 on y equaling our x squared plus c. Okay, when we rearrange that and when we sub in our y of 0 equals 2, so when our x equals 0 and our y equals 2, we find that we get c equaling a half. So what we do is we write this a bit better and say that we've got, we rearrange for y, so that we get y equals 2 over 2x squared plus 1, just by rearranging. Okay, when x equals 1, we get y of 2/3, okay, or 0.6667. Okay, so then we can do our percentage error and say we're 0.6079 minus our 0.6667. So we have 0.6667 times by 100. Okay, gives a percentage error, okay, of minus 8.8%. Okay, because we were smaller, where in the previous ones we were larger. Okay, I really don't think you'll have too much trouble on this section at all. It's just getting used to doing those iterations going through. Okay, keeping track of your results in the table is a good idea. Okay, but I really don't think you'll have too much trouble. Okay, because remember the answer that you get for all of these is the number that you end up subbing back in the next time, so you just got to keep going through that process. As I said, if we decreased our h value, our step, we'd have more steps to do obviously to get to the number that we needed, okay, but our answer would be more accurate. Okay, so if you want to do a bit of a test on one of these, give it a go yourself and say, like, if you halve your step size, okay, so you'll have twice as many steps, see what your value is and see how your percentage error changes. Okay, otherwise that's all there is to this video.